Hello everyone, my name is Arman and I'm a graduate student at University of California, Merced. Today, I'm very glad to present our work on training ensemble of bagged oblique decision trees using tree alternating optimization. This is joint work done with my advisor, Miguel Ángel Carreira Perpignan. So ensemble decision trees are extremely popular machine learning models which have been successfully applied in various tasks, including classification. In this work, we mainly focus on classification and consider bagged trees, where individual trees are trained independently on subset of data. However, method can be directly extended for other learning problems such as regression and other types of ensembling, like boosting. So in general, such forests have numerous advantages. They are able to achieve low bias and low variance, and therefore forests are considered as robust models against overfitting. They're easy to tune in terms of hyperparameters, and they are fast to train and generally scalable to large data sets. For example, each tree in random forests is trained independently, and therefore it is embarrassingly parallel. And often there are other advantages as well. However, there are some limitations. The first one, I guess, is that each tree in an ensemble is axis aligned. Well, that means each decision node tests only for a single feature, which by itself can be a limitation in some scenarios. For example, where correlation of features is important. Well, let's say if input is an image, looking only on one pixel at a time gives poor representation ability and typically leads to poor performance. Therefore, people usually apply some kind of feature transformations before fitting it to the forests or to decision trees. Second, such axis-aligned trees are usually trained using recursive greedy algorithms such as cart and or C4.5, which are shown to be highly suboptimal. In this paper, we address both of these issues, and our idea consists of two parts. First of all, we use more powerful and more flexible trees, such as trees having oblique splits and linear leaves. Next, we use an algorithm which can optimize such trees well. Our results show that even with a single tree, the improvement is dramatic in terms of accuracy and model size, and ensembling them achieves even better results. To do this, we built on top of recently proposed algorithm, tree alternating optimization, or TAO. And TAO in general finds good approximate optima of an objective function. And typically there are other advantages. And finally, we ensemble such TAO trees by training on a random subset of data or simply bagging them. Well, it's worth to mention that there are some other previous attempts on constructing forests out of trees that are beyond axis alignment, but their improvement is shown to be marginal over conventional trees. And moreover, all popular implementations of forests, like random forest or gradient boosting, XGBoost, and so on, use axis aligned trees. Okay. So let's first consider optimization of a single tree. TAO takes as input a tree, which is called capital T in this slide, with predefined structure. This initial tree is typically complete of depth delta with random node parameters initially. But we can also take a pre-trained tree obtained from other algorithms like cart. Next, we solve the following optimization problem on a given training set. Here, the loss function L can be any desired classification loss function, like hinge loss or logistic loss. And additionally, here we show that it is possible to use regularization term phi, which can penalize the parameters of each node, for example, by applying L1 penalty. Next, we define the following three theorems in order to solve the optimization problem in the previous slide. Details of the theorems and proofs can be found in the paper, but essentially the first theorem is a separability condition, which essentially states that non-descendant set of nodes, for example, all nodes at the same depth, can be optimized independently. This logically makes sense because first, we assume that nodes don't share common parameters, right? And second, a non-descendant set of nodes has disjoint set of training points at each node. This is because decision trees defines a hard partition, right? Because of the thresholding operator at each node. And therefore, each instance follows a unique root to leaf path. We also assume that the remaining part of the tree is fixed due to usage of alternating optimization. This allows the objective function defined in the previous slide to separate over any non-descending set of nodes, which is presented in this equation. For simplicity, here we show this for a pair of nodes, I and J. Now we can apply separability condition to train leaves and decision nodes. First, let's consider leaves. Clearly, leaves are non-descendants with respect to each other. By fixing the remaining parameters of the tree, we can train each leaf independently. And this equation solves the leaf optimization problem. Here, a small g is a predictive function at each leaf. Note that since each instance follows unique root to leaf path, the actual prediction is given by the leaf, right? So therefore, tree output here is replaced by g. But this predictive function applies only to the subset of points that reach that particular leaf. Therefore, this equation solves much smaller and simpler problem. If g is a linear function, then the solution would be fitting a linear classifier and possibly applying by some regularization. If g is a constant predictor, then the solution would be simply taking a class with the highest number of instances falling in that leaf, or simply saying majority vote. Similarly, we can derive optimization of decision nodes of a tree. Here, separability condition can be applied to any non-descendant set of nodes. For example, all nodes at the same depth. And here we present the single node optimization problem. And small f defines a decision function in that particular node. It can have only two possible outputs, namely right or left, because we use binary trees. Also, since we consider oblique trees, this thresholding function has a linear form. We also define here a loss function, small l in, as the loss incurred if choosing the right or left subtree. In other words, what is the loss value if I send this instance to the left or right child? Remember that we fix the remaining part of the tree, including all descendants of that node. Therefore, this loss can be calculated exactly, and node ideally should send the instance to the best child. That choosing best child can be formulated as the following equivalent binary classification problem. Here, y bar indicates which child, left or right, gives better error. So we encourage f to send the instance to the best child. Therefore, we can consider it as a pseudo label of that instance. Moreover, the binary classification problem here is weighted because the loss or error incurred by the instance is in general a real positive number that depends on the instance. But in this paper, we consider 0-1 misclassification loss. In this case, the binary classification problem would be unweighted. Okay, the given linear binary classification problem can be solved using any well-implemented solvers like linear, which also additionally supports different regularizations like L1 or L2 penalties. Okay, to sum up, here is a pseudocode for alternating optimization algorithm for training a single tree. So we repeatedly traverse a tree in BFS order and optimize all nodes at each depth, possibly in parallel since they're independent, while remaining ones are fixed, all descendants or all parents. Okay, if node is a leaf here, then we train a classifier either constant or linear on its reduced set, as it was shown before. If node is a decision node, then we solve a linear binary classification problem on its reduced set. Okay. One pass over all nodes is one TAO iteration. We keep iterating until some stopping criteria is met, like maximum number of iterations or error tolerance. Okay, and finally, given we can train a single tree, now we can collect them into a forest. There are multiple ways to do it, and we explore probably the simplest one, bagging each TAO tree into forest. Our primary goal here is to show that even such simple technique brings a huge improvement in terms of accuracy. We also wanted to make our algorithm really fast and scalable, okay? As I mentioned multiple times, we use oblique trees, oblique splits, and our leaves are either linear, as in conventional trees, or constant. We initialize, or constant. We initialize each TAO tree from a complete tree of depth delta and random node parameters. Additionally, we employ L1 regularization in both leaf optimization, if necessary, and decision node optimization to obtain sparse trees. This makes to use few features in each node. It also leads to more tree pruning, okay? And yeah, so here's our results in some standard classification benchmarks. More results can be found in the paper. And we compare our method with state-of-the-art forests like random forest and XGBoost and so on. We also compare with other more recent works. Here, capital T shows a number of trees and delta is maximum depth. As you can see, even single TAO tree can already perform well. Improvement is even better if we use linear leaves. But more interesting results are for TAO forest. And our experimental results suggest that they have the lowest test error in all datasets and often by a quite considerable margin. Moreover, our resulting forests have less number of trees and they are shallower. For example, in both of these datasets, such test error can be obtained using only 30 or 40 trees. Okay. And it's also true that our oblique trees use more parameters at each node. Therefore, we also report actual number of parameters and our estimates of flops for inference. Results can be found in the main paper, and they show that TAO forests have comparable model sizes, and this is partially due to sparsity penalty that we apply. And next, we perform more challenging experiment. We take a subset of ImageNet dataset consisting of 64 classes and use features extracted from VGG neural net architecture. Essentially, we take output from convolutional layers of the neural net and then use it as input feature. Okay, and here are the results, which are self-evident, I guess, and confirming our earlier results on standard benchmarks. We additionally report model complexity and runtime. We admit that TAO forests are slower compared to traditional random forests due to using alternating optimization iterations, but it has a similar runtime to that of XGBoost, but achieving lower error. And here we can see a trade-off between forest size and error for different algorithms. All of them reduce both training and test error as T increases, number of trees increases. Random forest and XGBoost even reach zero training error because the trees are so deep. In contrast, TAO uses shallower trees that do not reach zero training error, but greatly lower the test error, even with 10 trees, as you can see. In this slide, we explore the effects of various hyperparameters. The most important ones are number of trees, tree depths, and number of iterations. Overfitting, so the overall picture is more or less clear. Each tree should be trained for as many iterations as possible. Also, depths and number of trees should be as big as possible, but avoiding overfitting. Overfitting can be clearly observed at left bottom and middle bottom figures. Our analysis is not limited by hyperparameters. Diversity of individual learners is one of the key points beyond success of random forests. We also explore the effects of various diversity mechanisms. And some of them are specific for TAO trees. For example, we initialize each tree in an ensemble from different random initialization. And we observe that it brings some improvement. Details can be found in the paper. And as a conclusion, our idea here is to use more powerful oblique trees, which are better optimized thanks to our TAO algorithm. In this paper, we show that even simple ensembling techniques such as bagging, together with TAO trees, already shows excellent results, both in terms of accuracy and model size. Additionally, the proposed method is relatively simple to implement and use, and quite efficient in terms of runtime. All these make of TAO FODS a model of immediate practical applicability. And finally, I would like to mention that we have promising results showing similarly good improvements in regression tasks, and also with boosted trees rather than bagged trees. Thank you for your attention.